Hi students, in the last chapter we learnt about pure rotation, but in this chapter we are going to learn about rotation when translation is also taking place. In the case when a body is rotating and translation is also taking place, what is the velocity of each part of the rotating body? What is the value of friction force acting on the body? We will learn about all this in this chapter. Rotation 2, translation and rotation. So first of all, let us understand what exactly happens when both translation and rotation are taking place at the same time. We encounter this situation almost every day when we look at vehicles moving on the road. If you magnify the wheels of this bus here, what do you observe? You observe that the wheel is rotating with an angular velocity omega and it is also moving forward with a center of mass velocity v, isn't it? So in general, whenever we see bodies rolling as well as moving forward, they have an angular velocity also and they have a translational velocity also. In this case, let us study the exact velocities of different points of this rotating wheel. If you look at the topmost point of this rotating wheel, what will be the velocity of the topmost point of this wheel? The topmost point will have a center of mass velocity v, because since the center of mass has a velocity v towards the right, every point on the wheel is moving towards the right with a velocity v, isn't it? If every point of the wheel does not move to the right with a velocity v, then the wheel will be broken into parts with different parts moving with different velocities. So every part of the wheel is definitely moving to the right with a center of mass velocity v. Now since the wheel is rotating with an angular velocity omega about its center of mass, the topmost part of the wheel will also have a velocity omega r because of this angular velocity, isn't it? We had learnt earlier in the chapter circular motion that if a body is rotating with an angular velocity omega, then the tangential velocity because of that rotation will be omega r. So the net velocity at the top of the wheel will be the sum of the center of mass velocity and the velocity imparted because of the angular rotation of the wheel. So v plus omega r will be the velocity of the topmost portion of the wheel. What will be the velocity of this portion of the wheel? The point on the side. The velocity of this portion of the wheel will be v towards the right, of course, as is the case with all other points on the wheel. The velocity omega r will act downwards in this case, isn't it? Omega r represents the tangential velocity because of the angular rotation of the wheel. So this velocity will act towards the right. So this will be the net velocity vector of the point that is on the right of the wheel, isn't it? V will be towards the right and omega r will be downwards. The resultant velocity will be v vector plus omega r vector. For a point that's at the bottom of the wheel, the velocity v of the center of mass will again be towards the right. However, in this case, since the wheel is rotating in the clockwise direction, the velocity omega r will act backwards, isn't it? So the net velocity of the bottommost point of the wheel will be v minus omega r. If you look at the leftmost point of the wheel, this point will have a center of mass velocity v towards the right, but the velocity omega r will act upwards because of the angular velocity, isn't it? This velocity will act upwards because the wheel is rotating clockwise. So these will be the velocities at different points on the wheel. Understood? There is no doubt about it. So this is what happens when a body undergoes both translational and rotational motion. These are the velocities different points of the body have. Now there can be a very interesting situation. V is produced differently and omega is produced differently. You see, omega r is not related to v. Omega is the angular velocity, so some torque must be given to this ball or this wheel to produce omega. V is linear velocity, so some linear force must be applied on this wheel to produce v. But what if, coincidentally, v is equal to omega r? If that happens, we get a situation called pure rolling. Understood? In that situation, the velocity at the topmost part of the wheel will be 2v, because the velocity is v plus omega r, and since omega r is v, the velocity is 2v. Similarly, the velocity here will be v horizontally and v vertically. the velocity at the bottommost part of the wheel will be 0, because the velocity v to the right will be cancelled by omega r to the left, which is the same as v to the left, and this will be the velocity at the left portion of the wheel. This situation, when the bottommost point of the wheel has 0 velocity because v is equal to omega r, is called pure rolling. Understood? Pure rolling is in fact basically the situation when the relative velocity of the bottommost point of the wheel with respect to the ground is 0. So this is a special case of translation plus rotation in which v is equal to omega r. Understood? Note that when we say v equal to omega r, we generally mean the tangential velocity produced because of the angular velocity. In this case, when I am saying v equal to omega r, I don't mean that tangential velocity. What I mean is that the center of mass velocity of the wheel is equal to the angular velocity of the wheel into the radius of the wheel. Understood? So vcm equal to omega r in this case. The center of mass velocity of the wheel, which is not related to the angular velocity of the wheel, is equal in this case, v equal to omega r. So there you go. When the velocity of the bottom part of the wheel is 0, then the wheel will be said to be undergoing pure rolling. Sometimes pure rolling is also called rolling without slipping, or motion with no relative motion at the point of contact. Now I just told you that in case of pure rolling, the velocity of the bottommost portion of the wheel is 0, isn't it? However, this does not always mean v equal to omega r. Understood? Sometimes it could mean the relative velocity of the bottommost portion of the wheel is 0. It is not necessary that the absolute velocity of the bottommost portion of the wheel is 0. Understood? The velocity of the bottommost portion of the wheel with respect to the floor is 0. Suppose the floor itself is moving to the right with a velocity 1 meter per second. In this case, pure rolling will be said to occur when the bottommost portion of the wheel moves to the right with 1 meters per second. Understood? So that the relative velocity of the bottommost portion of the wheel with respect to the plank is 0. In this case, v might not be equal to omega r. In fact, v minus omega r will be equal to 1 meter per second in this case. You can even take sample values. Let's say the velocity of the center of mass of the ball is 5 meters per second. Let's say the velocity of the plank is 1 meter per second. Omega r, let's say, is 4 meter per second. In this case, the topmost part of the wheel will have a velocity v plus omega r, that is 5 plus 4, 9 meter per second. The bottommost part of the wheel will have a velocity v minus omega r, that is 5 minus 4, equal to 1 meter per second. Pure rolling takes place in this case because the bottommost portion of the wheel has the same velocity as the floor. Understood? So it is not necessary that v should be equal to omega r in pure rolling. In pure rolling, the condition is that velocity of center of mass minus omega r should be equal to the velocity of the floor on which the ball is traveling. Understood? So this is the perfect condition of pure rolling. Generally, because the floor is at rest, we always say that v is equal to omega r, because the floor is at 0 velocity, so v minus omega r should be 0 in general cases. So did you understand pure rolling? The crux of pure rolling, of course. This is what pure rolling is all about. Sometimes pure rolling does not take place, and then the ball or the disc or the wheel is said to slip on the floor. We just saw that when the velocity of the bottommost portion of the wheel is equal to the velocity of the floor, that is 1 meter per second, pure rolling was taken place. If, however, the velocity of the bottommost portion of the wheel is greater than the velocity of the floor, in that case, say it is 2 meters per second, in that case we say that forward slipping is occurring. Pure rolling is not taking place and the wheel is forward slipping over the floor. If the velocity of the bottommost portion of the wheel is less than the velocity of the plank, say the velocity of the bottommost portion of the wheel is 0 meter per second while the plank is moving forward with 1 meter per second, in that case we say that backward slipping is occurring. Understood? So when the velocity of the bottommost portion of the wheel is the same as the velocity of the floor, we have pure rolling. When it is greater than the velocity of the floor, we have forward slipping, and when it is less than the velocity of the floor, we have backward slipping. Understood? So this is what you must understand. Another important concept that you must understand in translation combined with rotation is the concept of kinetic energy in these cases. You see, in cases when our wheel or ball or body is rotating about its center of mass also, and the center of mass is also moving in translational motion, we have both translational and rotational kinetic energy. If you look at this particular body which is rotating about its axis and which is also moving forward with a velocity v, the kinetic energy of this body will be half I omega square plus half m v square. Half I omega square here is the rotational kinetic energy of the body, and half m v square here is the translational kinetic energy of the body. Here I is the moment of inertia of the body about the axis about which the body is rotating, and omega is the angular velocity of rotation of the body. Understood? So when bodies move translationally and they also rotate, you have to calculate both the kinetic energies, translational and rotational. So many concepts we've learned. To clarify all these concepts, let's solve a problem. Of course, to solve more problems related to rotational motion, you can always take tests at TopCoaching.com's physics section. This problem was asked in IIT JEE in 1999. A disk of mass m and radius r is rolling with angular speed omega on a horizontal plane as shown. You can see a disk here. It has an angular velocity omega and it is rolling on a horizontal plane. Whenever the term rolling is mentioned, you must understand that pure rolling is being talked about. The magnitude of the angular momentum of the disk about the origin O is half mr square omega, 3 by 2 mr square omega, or 2 mr square omega. The question is simple. There is a disk which has an angular velocity omega. The speed of its center of mass is clearly omega r because the disk is pure rolling on the surface. It's moving like this. We have to calculate the angular momentum of this disk about the origin. Well, we know that when a body is translating also and it's rotating also, in such situations the angular momentum is given by the expression L equal to LCM plus mr cross v. Here v is the velocity of the center of mass of the body, r is the distance of the center of mass of the body from the axis about which angular momentum is being calculated, LCM is ICM into omega. The moment of inertia of this rotating disk is clearly mr square by 2 about its center of mass. So LCM is mr square by 2 into omega. mr cross v can be written as mv into r, isn't it? Because the perpendicular from the axis to the linear momentum vector of this rotating body is r, the radius of the disk. Therefore mv, the linear momentum of the disk, has been multiplied by r, the perpendicular from the axis O to the linear momentum vector of the disk. So the net angular momentum is mr square omega by 2 plus mvr. Since the disk is pure rolling, therefore v is equal to omega r, or you can say that the net angular momentum is 3 by 2 mr square omega. That's our answer. So that was a simple question. Here's another question. This one was asked in IIT JEE 2004. A disk is rolling without slipping on a horizontal surface. C is its center and Q and P are 2 points equidistant from C. Points like this. As you can see, C is the center of mass of the disk and there are 2 points as shown which are equidistant from C. Let Vp, Vq and Vc be the magnitude of velocities of points P, Q and C. In that case, Vq greater than Vc greater than Vp, Vq less than Vc less than Vp, Vq equal to Vp, Vc equal to half of Vp, or Vq less than Vc greater than Vp. So basically we are given 3 points on a disk which is rotating and it's pure rolling also. And we are asked the relationship between the net velocities of 3 points on the disk shown. This is our rotating disk. P is here, Q is here. The distance CP is the same as the distance CQ. We have to find the relationship between the net velocity vectors VQ, VC and VP.